of where we left last time. Just sorry that I set the timer. Okay, so I already wrote some of the things at the Blackboard, but I think that this is something that, I mean, I hope it came across in the last lecture, that indeed, okay, here. So we are going to be dealing with the topic of supersymmetric black holes, because indeed supersymmetric black holes are amenable to microstate counting. So we have seen in many lectures, like, well, in Alejandra's lecture, not in my lectures, that indeed the black holes have a big entropy. And however, solution in general relativity is unique. So one is really bound to ask whether the states like that accounts for the entropy come from. So in the case of black holes with a dual field theory, which is, for instance, black holes which live in asymptotically area space, I'm sure that maybe Alejandra in this lecture also deal with other black holes, EDS3. I'm sorry that I was not there, but so basically when a black hole has an anti-de Sitter asymptotics, then you can map your black hole system into a theory, which in general, like, is given the holographic duality, is a theory in one dimension less. So in our case, we will deal with ADS4 black holes. This is the one that we studied yesterday. And the dual field theory will be a CFT3. I'm sure that maybe you're a bit more familiar with the ADS5 and CFT4. Well, okay, this is just the same duality, but in one dimension less. In particular, we relate, so the duality comes that it relates M theory, a reduction of M theory on the 7-dimensional sphere. This gives you a theory of 4-dimensional gauge supergravity, which has an ADS4 vacuum. And this is dual to a theory which is ABJM, which comes from the name of the people that discovered, Aaroni, Barman, Jaferis, and Maldacena. Was discovered in 2008 from a theory that comes from M2 brains. And it's a 3-dimensional superconformal Chern-Simons matter theory. And so in particular, it has lots of matter, it has supersymmetry. I can go into a bit more detail, but for the topics of this lecture, it's not really needed. It's basically 2 copies of Chern-Simons theory with opposite level K, and also some matter supermultiplets, coupled in a specific way. But okay, so it's like a theory. This correspondence is very well established. So we know what this corresponds to in this picture here. And indeed, since we want to really have precise holographic correspondences, we want to really count states in dual field theory, we really need to work with the systems in which holography is very well posed and very well established. And so indeed, in order to have, we are working on this because it's a precise holographic correspondence. And also, we need to work in theories of supergravity that indeed incorporate supersymmetry, because supersymmetry brings computational control. So indeed, we will find solutions that are supersymmetric black holes, and we're going to use supersymmetry, like supersymmetry localization, to compute the dual picture that is here. So for the structure of my lecture, I'm mostly focusing on the gravity side. So all this lecture will mostly focus on this. I will explain a bit how this works, but I will be mostly interested in the fact that interplay between these 2 pictures, focusing mostly on the gravity side. So yesterday we have seen how to construct a supersymmetric black hole with precise examples. So we have seen that indeed the fact that in supergravity you preserve supersymmetry amounts to the fact that the solution is for sure a solution to the equations of motion, but also is invariant under supersymmetry variation. And to do so, we have imposed that the supersymmetry variations of the fermions, which were the gravitino in our theory, the supersymmetry variation was set to 0 for a specific supersymmetry parameter, which is called epsilon. So maybe in the lecture, I already mentioned this epsilon, once it's a solution to this equation, is called the killing spinor of your solution. So maybe this I forgot to mention, but this is like killing spinor. And this whole equation is also called the killing spinor equation. And the solution that you get, so they are supersymmetric black holes, they're also called BPS black holes. Because in general, in asymptotically flat space, they satisfy a bound, which is called the Bogomolny-Prasad-Sommerfeld, which in flat space correspond to the extremality bound. But we adopt the same nomenclature, so if I by mistake, I mean, I say BPS, I mean supersymmetric black holes, still in this setup. So setting the supersymmetric variation of the gravitino to 0, indeed, it means that we have to first find a supersymmetry parameter, and this will also constrain the bosonic fields in your theory, in particular the charge of your black hole. So the metric is always the same that I wrote many times. And I call it like this, so the work factor, I leave it generic, plus r squared the omega 2 squared. And then, so V of r equals g squared r squared minus 2m r plus, this is z squared over r squared. Z squared equals q squared plus h squared, where gauge field, temporal component of the gauge field is q over r, and the phi component of the gauge field is h cos theta. So this is the magnetic charge of your solution. This is the electric charge. So we have found first a solution, but in reality there are many different, well, there could be different branches of solution in general for superiority theory. This is what happens also here. I showed you the easiest example. So there are actually two different ways of preserving supersymmetry. So the one on the left, I found it yesterday. For this one, I will tell you that also exists, but we'll mostly focus on this microstate counting on the solutions that we found yesterday, because we are kind of familiar with them. So just to refresh your mind, so the first let's say, way of preserving supersymmetry is, as I was mentioning yesterday, this the so-called topological twist, where we cancel the spin connection, like we have the Killing spinor that did not depend on the angular coordinate, and we just made various terms in the SUSY variation cancel just by imposing some projections. So, and these solutions here were in the original paper by Roman. It was dubbed the exotic monopole solution. So if you remember from yesterday, we had that after solving this equation here, we were left with constraints among the parameters, which are this one, m equals 0, and we had also a constraint on the magnetic charge. The magnetic charge had to be 1 over 2g. So with a bit of effort, like kind of a lot of effort, but you can still do it, you can also show that this configuration here is still supersymmetric if you add electric charge. You have to a bit modify your ansatz for the Killing spinor here. It's quite complicated, but I can teach you how to do it if you want in the exercises. But it's something that you can also add electric charge, and it turns out that the electric charge is unconstrained. But for the moment, so in most of the cases, we will work only with a purely magnetic configuration because it's the easiest setup. So we'll see that if you plug in, so first of all, if you plug these two values here inside, or even if with Q inside here, you see that you already encounter a problem. So let's do it together. So V of R, if you plug in these values here, you get something like this. 1 over 2 GR squared plus Q squared over R squared. So using this can be a black hole. So a solution of this form can be a black hole. Well, the answer is no. You remember that in order to be a black hole, a solution needs to have an event horizon. This means that you have to find that 0 of this function here. But you see here, this function here is just a sum of terms which are positive, right? So it can never vanish. So it means that the horizon can never be there. You only have the singularity at r equals 0. So this thing will be cured when you go to matter couple. So that's all, like in the future, like in the last part of the lecture, I will also tell you about solutions which are supported by scalars. And this will be something that will be different. So adding scalars, you can have actually a horizon on your configuration. But as for just sake of simplicity, we are just going to work with this solution at the moment. So in general, so for this solution here, you have that Killing spinor does not depend on the angular coordinate. Theta and phi. And this means that the supercharge that you get in the algebra will be invariant under rotation. This is also a solution that preserves 1/4 of supersymmetries. Maybe I'm gonna continue in this term here. So again, all of this, the solution is 1/4 BPS. Because we have assumed that there are two projectors on our Keeling spinner. And also another thing that I wanted to point out is that indeed, so this particular value of the magnetic charge is exactly peculiar because by doing this value of the, by taking this value here, we are satisfied the Dirac quantization condition. So there are some fermions in the system, particularly they are gravitinos. And these gravitino carry charge exactly like carry charge G, actually 2G. So then the Dirac quantization condition, like, well, basically the charge of the gravitini multiplying the magnetic charge of the black hole gives an integer. And this integer is exactly 1 because the charge is 2G. Yes? In this case, so you don't see it from here, but so yesterday I showed you the full Lagrangian, well, bosonic Lagrangian, plus I wrote the Rarita-Schwinger field, so this is the equations of motion for the gravitino. If you see there, the gravitino is charged and has electric charge, which is 2G. I didn't show it here, so you have to trust me for that, but yeah, if you go on the paper, you look at the full Lagrangian, you will see that the gravitino has electric charge, because it appears in the covariant derivative.
Sorry,
yes.
A question. Since we don't have an horizon, we don't have a chemical potential at the border, right? I mean, because we have only electric field with no chemical potential, and if we don't have an horizon.
Yeah, exactly. So the event horizon, sorry, the chemical potential is given by the difference between the gauge field at the horizon and the gauge field at synthetic infinity, if you want.
Yeah, but like synthetically there goes to 0, and since we don't have an horizon,
yeah, these are naked singularities. So for naked singularities, you don't have a consistent, let's say, they're not consistent thermodynamic systems. So this naked singularity, they will be the ones that if you add higher derivative corrections to your action, they will obtain a horizon. But then you need to take into account further terms in the Ricci scalar and so on and so forth. At just the classical level, they just don't have a horizon. But the solution that we're interested in will be a minimal modification of this with the same properties supersymmetrically, so we will and they will have a horizon, the ones that we will really be interested in. One last thing is that, so if you remember correctly, so in the supergravity Lagrangian, the cosmological constant was parametrized by G. So 3G squared minus 3G squared was the cosmological constant. So if we try to take the flat limit of this solution here, you can see that you encounter some problems. So this solution here is something that arises only in asymptotically ADS spaces. And it's something that was discovered also much later with respect to their asymptotically flat counterpart, because indeed the structure of how the supersymmetry works is very much different. So G equals 0 is a flat limit. It switches off basically the cosmological constant, but this is not well defined. Your solution indeed blows up. And as I was mentioning also yesterday, all the solutions here can be uplifted. We have formulas for uplifting these solutions to 11 dimensions. And the solution will be made by M2 branes wrapping the horizon. Once you have a horizon, I mean, wrapping the two-dimensional horizon section. Okay.
Just to remind myself of what we saw yesterday. So yesterday, you assumed this V of R, and you checked the Keeling spinor equation, right?
I checked for which values the Keeling spinor equation is satisfied. And given the ansatz that I made for the projection, I found out that these were the values. So I put this to 0 for simplicity previously, but I checked that if I impose these with the two projections, the solution that I get is this one.
And let me remember. So But there you plugged already the form of V of R, right? In what we did
Exactly,
yesterday.
because I wanted to work with very simple solutions, which are the static spherical symmetric. They're not the only one, so I'm going to explain you that they are.
But no, my question was, if I did not know what V of R is, could I find it from what we did yesterday? Couldn't I just find what is V of R such that this killing spinor equation is satisfied?
Yes, yes, you can do that. Many times you can do that.
That's
when
how
you
we
don't
would do
know,
it, right?
when you have, for instance, when you have scalars, you're solving for theories with more matter fields, like different couplings. In general, you don't have this sort of ansatz. I want this sort of ansatz because I know that the ADS Reister-Nostrom solution is the only one with the boundary S1 times S2 in this theory of Einstein-Maxwell lambda. I know that this is the only solution, so I can just use this and then check the parameters.
So, and if I had not made any commitment to any V of R and follow the same logic, would I still reach this conclusion that it would only work for this V of R with this choice of mass and magnetic field?
Yes.
Okay. And one more question about last time. So last time you checked the equation, this d theta equation, right?
Yes, I checked
Wasn't
only.
there other components of the equation to check?
Yes, I left it for exercises.
Okay.
So yesterday we did this thing for theta. You will see automatically, well, now I think for the sake of time, maybe I should not do all the components. But indeed, this is like the killing spinor equation is like it needs to be satisfied for all the components, theta, phi, RT. The phi component is also pretty straightforward. It's very similar to the theta. From the R component and the T component, you get the killing spinor dependence on the radius and on T. But the important thing here is that it would not depend on theta and phi.
Okay. So that means that with this amount of supersymmetry, we don't have black holes, right? Because these are not a black hole, as you said.
Not in this theory. If you are looking for solutions with a spherical horizon, I will tell you later because there will be some other solution. If I change the spatial section of your metric, if I place it instead of being on an S2 on an hyperbolic to space, then I will have solution with a horizon. This is the next step that I'm going to show.
And these solutions that we are finding, are they solutions in this?
Exactly, yes.
They are the solutions here? They are?
Yes, in a specific truncation, in the smallest truncation that you get from a theory on S7 times ZK with K equals 1. Because it's a truncation that fits into n equals 8.
But it's not a physical solution as you explained. So
no,
I
exactly.
should not try to interpret this solution as some state in ABJM. That doesn't make sense.
No, exactly. As of now, no. I will see like in a few minutes that we can, starting from this seed solution, that was the one that was historically found, we can modify other work factor, or we can also add scalars. We get good solutions that have a horizon, and on this one we can do the microstate counting. But I wanted to first show what you can have just by solving the killing spinor equation with a very simple solution here before introducing scalars or other things. But yes.
Let me see. Okay. Your theory originally is supersymmetric, right? And you find the equations of motion, and you said, I'm trying to follow the logic, that you were, for simplicity, I guess, you were interested in solutions in which the fermion fields are absent.
Yes.
So if I start with that field theory, I found the equations of motion, you turn off the fermions. What is the argument that you want to keep the supersymmetry in the equations of motion?
No, so I solve the equation. So I have a Lagrangian. I vary with respect to the metric. I get the Einstein's equation, Maxwell equation. There will be also the Rarita-Schwinger field, so the gravitino. I solve its equation. It's like a Dirac equation. And then I impose the fact that the supersymmetry variation of the fermions and also the supersymmetry variation of the bosons are 0. I will have additional equations because basically, so, I mean, now I'm taking only this equation because the supersymmetry variation of the bosons are proportional to the fermions that I set to 0.
Yes.
If I don't set the fermions to 0, I will have another equation to solve, another SUSY equation to solve, and also the equations of motion for the fermions.
Okay, my doubt is the following. Why do you need that in the equations, the solution that you're choosing of having zero fermion fields, why do you need this requirement of SUSY? It seems to me something by hand that you're imposing by hand.
Because then I want to study the technology that I have in dual field theory. They are available to study supersymmetric ground states. So I want the same. So I'm counting supersymmetric states in this dual setup. Then I want the same supersymmetric structure to be visible in my solution.
Because of the requirement of the duality?
Yes.
Okay.
Exactly. So that's why I need to work with supersymmetric backgrounds.
Thank you.
Okay, so let me maybe speed up a bit. So given the projector that I had here, these solutions were valid. There is also another solution that I'm briefly mentioning here, because indeed, so you can impose different ways of preserving supersymmetry in this side here. This would correspond to either this solution or this. The main lectures will be on this. But just to just mention that there will be also another solution. So this is the exotic monopole. This is the ADS Reister-Nostrom. So let's see, put it here, ADS Reister-Nostrom electric solution. This is parameter, and this, so you can preserve supersymmetry also with a different projector operator in the Killing-Spinor equation. It's a bit more complicated, honestly, but then the solution becomes 1/2 BPS, so you have to impose just one constraint here. It is again a naked singularity. So as you can see, from plugging this thing inside here and imposing also H to 0, you don't find any horizon. Something? No, you can ask if you want. And again, so this also uplift to 11 dimensions as some sort of rotating M2 branes. The Killing-Spinor will have angular dependence. And contrarily to what happens for this sort of configuration, if you add scalars, for instance, or if you change the topology of event horizon, the solution here doesn't really have a horizon. In order to make it a real black hole, you have to make it spin. So you cannot work just with this simple ansatz here. You have to find a more complicated metric, but this is something that also people have studied. So there are two different superalgebras with two different BPS bounds that also we have studied quite intensely in our paper that underlie the fact that you have these two different Killing-Spinors. And also the description at the level of the dual field theory will be that the solutions that generalize this will be described by the topologically twisted index, some sort of different partition function. For this one, they will be described the superconformal index, so two different objects. Just mentioning because many papers also appear in the archive, they are also about this. But the solutions are a bit more complicated, so we're going to focus on this one for the time being. And OK, so let's go on now. So we are interested in, so as I was mentioning, we are interested in these solutions here, but we're interested in the solution with the horizon. So what do? Well, the simple thing that we should do in order to, and I forgot that on this side, solution are 1/2 BPS, and they have a flat limit. And the flat limit, like in comparison to this one, the flat limit is well defined, and if you send G to 0 here, you get just the supersymmetric Reiser-Nostrom in asymptotically flat space, which is a configuration that is very, very well studied. But so, OK, so let's go on now. So we're going to generalize these solutions here because we want to have the smallest, let's say the smallest solution on which we can actually, from which we can say something about, about their states via a computation in the dual field theory. So the easiest thing that we can do for this solution to have actually an event horizon is to change the topology here. So it turns out that a solution like this, that are like I keep this warp factor here. I change this solution here. Maybe I can just erase everything so then I have Blackboard ready. So I can just modify the solutions that we have found yesterday in a very minimal way. So it turns out that in asymptotically ADS space, or at least in asymptotically ADS4 space, you can have solutions which do not have only spherical horizon, but you can have, for instance, black brains. So it means you can have black hole which have a horizon, which is an infinite two-dimensional plane. But also you can have solutions where the horizon is hyperbolic, two-dimensional hyperbolic space, whose warp factor reads like this. So instead of having sine squared, you have sinh squared theta d phi squared. So this is two-dimensional hyperbolic space. A phi is modified appropriately with the cosine hyperbolic. So this is also a solution to the equations of motion. And the warp factor comes with a minus sign. G squared R squared minus 1 minus 2m over R plus, I just focus on the magnetic solution, H squared over R squared. So the BPS conditions in this case read like this. So we do the same thing as we did yesterday, just with the same projections. We just plug in this metric here. I'm not going to do it for brevity, but what it turns out is that these are the conditions for the solution to be supersymmetric, and then 2GH equals minus 1. So in general, you can, the formula that constrains your magnetic field is basically saying kappa, where kappa is the curvature of your event horizon. So if your event horizon is a sphere, or the spatial two-section that you have here is a sphere, you get that H is equal to 1 over 2G. If it's hyperbolic to space, because it has a constant negative curvature, this is minus 1. If you want to have like a plane, instead this is 0. Well, so okay, just to give an idea, for these configurations here, we're going to have the minus sign. So if you plug in these parameters here, you automatically see that the warp factor is a square. It's GR minus 1 over 2GR. And is this a black hole? Is this an extremal black hole? Yes, because you can have a non-trivial horizon, like you have a horizon here. So the horizon, this solution here has two horizons at 1 over square root of 2G. This has two coincident horizons at this radial coordinate here, which means that your solution, if you remember, extremality was when two roots of the warp factor coincide. In this case, you have that the temperature is equal to 0, but your solution still has entropy. So just by modifying this warp factor here, going through the same procedure as we did yesterday, we find a solution which actually is extremal. So this is a good solution. It preserves supersymmetry, it has a finite area of the event horizon, and it's something from which we can actually compute something in the dual field theory.
It's just changing the answer we are using, or going to recording the warp factor. That's some interpretation from the compact distribution that we did on higher dimension.
No, in general, this is a solution of 4D. I mean, of course, if you uplift to 11 dimensions, you will uplift this entire 4-dimensional metric. And so this form will trickle into 11D, but it will not touch the 7. Like the reduction stays the same.
Okay, so it's just an answer. You're changing the answer.
So let's say that this is still a solution of your 4-dimensional theory that you get from the reduction of M theory down to 4D. So it's another solution to the Einstein's equation that preserves supersymmetry. Similar to what we did yesterday, let's say. So this hyperbolic solution is something on which we can work on. And also, so the solution is extremal, which means that the near horizon geometry is ADS2 times H2, right? So you have an ADS2 factor because the solution is extremal. So the solution interpolates between ADS4 asymptotically. So for R goes to infinity, you have ADS4. And in the near horizon geometry, you have ADS2 times H2, where H2 is the hyperbolic two-plane. Of course, here, in order to do all these computations in localization, you need compact manifold in general. So what are we going to do? We are going to compactify H2, so the hyperbolic plane, in a higher genus Riemann surface. The same thing you can do, for instance, with flat two-dimensional, with the flat two-dimensional plane. You can compactify it. You can basically identify the extrema, and you can get a compact manifold out of it, which is the torus, right? It's a bit similar to what Alejandra was saying a few lectures ago. So if you have a manifold of negative curvature, you can compactify this. Again, the same, basically by identifying appropriately, like some regions in your domain, you can have a higher genus Riemann surface. So this can be compactified. And you get ADS2 times sigma g, where sigma g is a two-dimensional constant curvature higher genus Riemann surface. Can imagine as some sort of a donut, something with many handles, something that generalizes a torus, but something two-dimensional, which we kind of know mathematically very well. Like it's a variant, it's like it plays the same role as a sphere, but it has more handles. So these were solutions that we're going to work with. So let me just, before moving on, mention that in this. So all the topological twists, all the Killing-Spinor equation that I showed you before can be generalized into many different ways. For instance, exactly the same physical structure arises, for instance, for black strings. Which will be configuration that interpolate, for instance, between ADS5 and ADS3 times sigma g. This is something that a lot of people have studied. Or, for instance, again, other configuration that, for instance, interpolate between ADS6 and ADS2 times sigma g1 times sigma g3. I'm sure that some people in the audience know maybe some of these solutions. And in general, you can also add many different charges, nut charge, angular momentum, and so on. But so you can add all the bells and whistles that you want to the solution, but this is a bit the building block. So in general, so for this solution here also, once we have this, you can compute the entropy, right? Because I mentioned zero temperature, but non-zero entropy. And the entropy is just given by the area of the event horizon divided by 4G. So for this solution here, we have the entropy of black hole, which is the area over 4G Newton, which will be equal to G minus 1 over 2G Newton. So from now on, I'm sorry that I will call, so the G that it's here, I should put it like maybe boldface. The G here is the number relative to the genus of your Riemann surface, not to be confused with this G here, that from now on, I will set it to 1. So this G here is basically your cosmological constant, G squared, so I'll set it to 1 now. So it will be minus the cosmological constant because we are in ADS, but so it will be G equals 1. The G that I put here, like this boldface G, is just refers to the genus of your solution. How many holes has your manifold? And in doing this, I have used the Gauss-Bonnet theorem that maybe, I don't know if you are familiar with, but basically states that the area, well, okay, you can do a bit of passages, but basically the area of a higher genus Riemann surface, like you can do that via the Gauss-Bonnet theorem is just 2G minus 2. So using this, okay, I'm going to call it Gauss-Bonnet. Okay, so we have a configuration which is supersymmetric, which has a particular value of the entropy, which is proportional to the area. However, you have that due to the holographic correspondence, basically the standard holographic dictionaries relates partition functions. So relates the partition function of a BGM that will compute that, for which there are techniques valid to compute that, with the on-shell action of your gravitational configuration. So rather than relating the area of our configuration, we will need to compute really the on-shell action. The on-shell action is a thermodynamic potential that we have encountered many times, right? We have encountered this on-shell action when we did, like, for instance, the computation of the Hawking page phase transition. Alejandra yesterday told you, indeed, she computed this on-shell action that comes into the gravitational path integral, and it's something that gives you an idea of how your solution behaves thermodynamically. So we'll see that for the on-shell action of these solutions, so the on-shell action of this solution here has a really very remarkably simple form with respect to their entropy.
Chiara, one question, sorry. I blinked and I missed it. Could you say again why instead of computing the area, you compute an on-shell action?
Because the standard holographic dictionary tells you that the free energy of a BGM, that is something that you're computing via localization or via some index, meaning counting states, is related to the thermodynamic potential, so the on-shell action of your gravitational configuration. But we'll see that the on-shell action has a very simple relation to the entropy. But we need to do this passage in order to relate these two things via the holographic dictionary.
Thank you very much.
And the point is that for this sort of configuration, you know, like we have solution at 0 temperature. So basically, if you remember in your on-shell action, it means that we have to integrate from 0 to beta, where beta is 1 over temperature. So I'm going to do the computation now. But a problem that automatically arises when you work with extremal solution is that your extreme of integration, in particular the temporal one, is infinite. So in general, the value of the on-shell action, your thermodynamic potential, suffers from divergences. So what we're going to do now, we're going to take a very let's say, accurate limit to this BPS solution and see that indeed the value of the on-shell action, like once you take the appropriate BPS limit, even if you define it this way, will be finite. So we're going to compute. So in order to relate this to a computation in dual field theory, we need to compute the on-shell action. Of this configuration, and we are going to work, since these are the solutions that actually have a horizon, we are sticking to this solution from now on. So the on-shell action, and we need to compute the renormalized on-shell action. And I think that from all these lectures, what you, given what you came across, is that indeed, so in order to compute the on-shell action, we need to sum, so the value of the action once we plug in the solution, right? So this will be Einstein-Maxwell lambda, plus also the counter terms, right? So we have some counter terms and also boundary terms. This is something that, for instance, yesterday Alejandra was mentioning. So we're going to take the solution and plug the value of this solution inside this 16 pi gn for x square root of g. Again, r plus 6. I set g, the coupling constant, to 1. So this is the cosmological constant, minus f squared. Plus we have the counter terms. So these two counter terms here will be in this term here. Will be boundary counter terms, so made out of curvature invariance of the boundary. So we have, first of all, the Gibbons-Hawking term. And then we have the Ricci scalar of the boundary. That depends on the boundary metric. So let me specify what is this. This is gamma is the boundary metric. And kappa is the extrinsic curvature. okay? So this is exactly the thing that Alejandra was doing like yesterday. So you take the action, you plug in the solution. You actually need to see that if you send R to infinity, like you have to integrate R from the horizon to infinity, you get divergences, but these divergences are cured if you add these counter terms here. So for sure, if you remember, kappa needs to be included because we want a system with Dirichlet boundary condition. We want to impose Dirichlet boundary conditions on the metric. So this kills the derivatives that you have of the metric. So then you, at the boundary, you fix only the value of the metric. And these other two counter terms, this is just a constant, and this is the Ricci scalar, the three-dimensional Ricci scalar, so it's the Ricci scalar of the boundary metric, also takes away some of the divergences. I'm gonna go here then. So for these solutions here, the temperature, let me just write it here. Or maybe I can put it here. So notice that the temperature is equal to the derivative of the work factor over 4 pi evaluated at R equals R plus. And this is equal to this. 1 over 2 pi. Okay. So for the BPS solution, which is the one that we are interested in, R BPS equals 1 over square root of 2, and M equals 0. Okay. So what we're going to do is that we're going to compute this on-shell action here. So we're going to like put this thing here, I is equal. So we have to integrate, so we have to plug everything in, and we integrate with extrema that go, for instance, so from 0 to beta dt, from R plus to cutoff R0 dr, and then again like theta and phi that are like we choose appropriately the extreme of integration in such a way that their integral is just this one. This is not, it's the Euclidean on-shell action. So I will need to turn this thing into Euclidean signature. So T goes into I tau, into this configuration here. And I'm not plugging in this yet. I'm plugging in just the general solution with temperature for the moment.
Excuse me, if the mass is 0, what is the thing that is radiating temperature?
Sorry?
If the mass is 0,
Oh, no, this one is, no, this is just for the BPS solution. So in this computation here, I'm going to compute the on-shell action for a generic solution where, for a generic solution that has temperature, and then I'm going to expand around this value here. Okay. So the upshot of this is that if I plug this solution here directly into this action here, naively I have a divergence because I will need to integrate between 0 and beta, and for the BPS solution, beta is infinity, right? Because we have 0 temperature. So what we're going to do is that we're going to plug in the general solution, and then we're going to expand it around the values here. So all in all, so we perform all the integrals on, and then what we get is this one, is this expression here. Where beta is 1 over t. And so putting all the pieces together, expanding around these values here, we see that we get like, so for the BPS solution, we expand around BPS values. And I put like a star here. So these are the BPS values here. Yes, I think so. Yes. Yeah, let me double check on the other notes. Okay, I have the notes there, but I can. So once I got this expression here, I can take the limit to this one, and remarkably, I see that the on-shell action is finite, and the thing that I get is this. So I expanded around the value -1/2 in charge, which is the value of the BPS solution, and around the mass, which for the BPS solution is just 0. So I expanded this thing here around this. And what I get is that the non-trivial term here is exactly equal to minus the black hole entropy, if I didn't make any typos. Okay, there is a minus in front, but basically means that the on-shell action of the black hole, which is related to some computation that we're going to do in the dual field theory, is also related via minus sign to black hole entropy. So we are justified in saying that the black hole entropy that we get, that we want to explain in terms of states, can be related via, like actually can be related by a computation in the dual field theory for the partition function of a BGM, by making this kind of, this careful limit. So now that we have set the stage, let's say we have a solution which is supersymmetric, we have seen what their thermodynamic potentials are, and now we are ready to compute things on the dual field theory. So I will be very brief on that, but I will sketch you in general what will be the general, let's say, the flavor of the computation that you have to do in the dual field theory. So in general, so we want to retrieve, yes?
The genus, you will have it from the compactification or already
So the
in four-dimensional?
So the genus comes from the compactifications of this horizon manifold here. So since the horizon manifold is a negative, has negative curvature, constant negative curvature, the genus needs to be bigger than, strictly bigger than 1. It's from the Gauss-Bonnet theorem.
But you don't see this in the four-dimensional metric.
So this is the four-dimensional metric is this one. So the solution solved the Einstein's equation and in the BPS equation with this metric here, where this is the metric of hyperbolic to space. Then, since it's better to work for localization, for instance, with the compact manifold, this will be, we are compactifying this spatial section here.
Yes,
So let's say before we were working, let's say we are interested in working with solutions which have, for instance, a black hole with a spherical horizon. But we found that for like the supersymmetry variation conspired and create a naked singularity. But here, like if you repeat the procedure with a solution with a hyperbolic space, you get an event horizon which is well-defined.
So that R is a kind of distance in four-dimensional or 11-dimensional? The R squared.
Okay. I think that no. This is just the four-dimensional metric.
Okay. So
the compactification, the compactification that I do here has nothing to do with the compactification that I do on this two-dimensional space. Maybe that was the.
Okay.
That was the.
It's related to that. Thank you.
Okay, if you need. Okay, here I'm just saying I have a solution that with this metric here, but I just want to take this space and identify some parts of the space to make it compact. It's like instead of having two-dimensional plane, I make it into a torus. into a donut, so then you have a compact and finite volume. So this will be handy because mainly in the localization procedure, you have to impose some boundary conditions, and these are imposed better in just extending this to localization on non-compact spaces. So okay, we have, so let me just, I think I'm running a bit behind, but so the formula that we want to discuss is this one, and we know that this is equal to minus E on shell. And we have reason, via the ADS-FT correspondence, to believe that actually we can get this value of the on-shell action for the black hole, which is equal to minus the entropy, via dual field theory computation. So if we get this, it means that we can actually track what are the states of the black hole in terms of a system without gravity, where we actually know how to do computation. It is a complicated system, lots of supersymmetry, lots of stuff, but it's something where we actually know how to compute states, we know how to compute the partition function. So how do we compute this partition function? I'm gonna just sketch the computation and the flavor of how people do it. Many people that over the years, starting from the, I guess, 2008 or even before, did this. And so they use techniques which is called the supersymmetric localization. So which is a field theory technique. So this is a technique now, we are in this side of the correspondence. Before now, we did all these things with our black holes. Now we see, okay, we have a quantity that we should compare to the dual field theory. We're gonna work here, and I'm gonna sketch which techniques you can use here to compute the partition function. So these allow to reduce an infinite dimensional path integral over, let's say, over a finite one, over a finite dimensional one. So if you want more details on that, I think a good basic introduction is a review of, well, there is a review by Pestun, but I think the simplest entry point is a review by Marcos Marinho. I didn't put maybe, okay, well, lectures on localization. And for just application to black hole physics, there is a review by Zaffaroni, where you can find also a lot of other details on the solutions. And it's, again, lectures on microstate counting. Okay, I'm gonna, on black hole, microstates. Okay, so supersymmetric localization, like, takes into account for a theory. So we have, let's say, a theory which Lagrangian S, and I collectively note all the fields in the theory by phi. So imagine that you have, so consider, so delta, which is a Grassmann odd symmetry of the system. Let's see the action S of phi. It smells a bit like something like a fermionic operator, which is a symmetry of your theory. It smells a lot like supersymmetry, right? That's what we introduced yesterday. But so we consider this, like we assume that this is also non-anomalous. This means that the measure in the path integral is also invariant. So, and also we impose, like we assume, the fact that this symmetry here, this operator here, squared to LB, another operator, which I call LB, which is a bosonic Grassmann even symmetry, of the theory itself. So for instance, could be Lorentz plus a gauge symmetry. So then we are going to consider, so imagine that your theory has an operator delta, which is a symmetry that squares to another symmetry, which is a bosonic symmetry. Then we can compute the path integral or the partition function. Z, so partition function of your theory is defined as this one, d phi, so these are the fields collectively denoted as d phi, e to the minus s. But I want to deform my partition function, so I want to introduce another parameter, so I want to make this depend on parameter t, which is a real parameter, and I add here another piece, which is this one, t delta v, where v is again, so it's a Grassmann-Odd operator invariant under LB. So these are all assumptions that I make. So I have an action. Imagine I find an operator like this that squares like this, and then I choose V as an operator which is invariant under LB. Then I have that if I compute dz over dt, this actually is 0. Because, so the first differentiator brings down this thing, brings down this factor here, right? Minus t delta v, but this can also be rewritten as this. Delta of v e to the minus s minus t delta v. And this is equal to 0 if you assume appropriate boundary conditions. So it means that I have deformed my path integral by a parameter t, but I deformed it in such a way that actually the partition function doesn't depend on this parameter. This is a very particular kind of deformation. So it means that the original partition function was at t equals 0, right? So this was the partition function of the original theory. So z t equals 0, it's the original one. But since the partition function doesn't depend on t, I can also compute it for arbitrary value of t. I can decide to compute it at value of t, which is plus infinity, for instance. So in doing this, by the way, we have used the fact that the measure is invariant, but also we have used in showing this line here, and hence this last line here, we have used the fact that the V operator is indeed invariant under LB. So I needed to use this in order to show this last equality. So since this thing doesn't depend on t, then I can also compute z of t at t goes to infinity, right? Because it doesn't depend on t. So I can choose where to compute it. And this gives a lot of simplification, right? Because when t goes to infinity, this term here goes to minus infinity, which means that the only term that survives, like the only configuration from which your path integral gets contribution from, will be the one for which delta v equals 0. And this is called the localization locus. This, of course, happens if delta v has positive definite bosonic part. But yes, we assume also that it's the case. So in general, your path integral then localizes, so z of t localizes at locus on configurations, meaning in which delta v, the bosonic part, is equal to 0. So instead of computing this nasty path integral and so on, I show you that this one reduces into a sum of configurations which satisfy this. So I just need to compute as like the contribution to this integral here comes only from the configuration that satisfy this, that in general are a finite dimensional space. There are few of them. So in general, this means that an infinite dimensional path integral gets contribution only from a few one, which is what localization does for you. In general, when you have to compute the partition function, then you will have like the sum over this BPS locus, so there will be some or saddle points, e to the minus s classical, and then you'll have one loop determinant of fermions over the determinant of bosons. These are the one loop determinants of the fermions and the bosons. But what counts here is that you have to compute this only for a limited number of configuration, and gives the full path integral. In general, I think no, it's not. I mean, so it, of course depends on what is your symmetry here, and in general, I assume that the examples that I have, which are very limited, this is just the supercharge. And then I think you can have, yes, in general, you can have different operators here that satisfy this. You choose one. Yeah, I think that in general this is, so I think I'm mistaken, but I think that this is something that is ensured probably from the fact that your theory is supersymmetric to start with. So in general, this works like in theories that you have supersymmetry because you assume that this is like the supercharge. So I'm assuming that the thing that you're saying is pretty much taken already care of if your theory that you start with is supersymmetric. But yeah, I will need to think about it a bit more. It's okay. So if you go through the entire procedure, so in general, then what you need to do, what people, like other people, not me, but other very, very good experts did is like compute indeed all the partition functions of all these theories which have holographic dual on many different manifolds. So you have to compute the one loop determinants of bosons and fermions. In general, supersymmetry guarantees you some cancellation. So this in general is a nasty object, but with help of supersymmetry, it collapses quite a bit. There are many different ways of computing this partition function via localization. You can also reduce your theory to 2D. You get like a system. Like in order to solve the partition function, you will need to indeed like perform a complex integral. So you do lots of like residue, like you compute lots of residues, so on and so forth. But in general, what you get is like an answer for the exact form of the partition function. And then you can expand in various different terms to make contact with what you had in the gravitational expression that you want. And so the partition function that so people, like I think the first people computing the partition function of a BJM via localization for the dual system to the black hole were Benini, Christov, and Zaffaroni. So by using all these technologies, we have to take a BJM. So a BJM is a three-dimensional superconformal Chern-Simons matter theory. You have to place a BJM on a rigid manifold because you have to make sure that the boundary of your black hole is like this theory here lives at the boundary. And so the boundary of your black hole, the Euclidean boundary, is S1 times sigma g. And also, so your rigid background, so it means that all the couplings that are in this matrix here, they will be, let's say, made by the rigid background on which you compute the partition function will be the one that has this geometry here. And also you turn on a background flux for the magnetic field. Which is exactly equal to the magnetic field that you have here. So magnetic field, which we call it also here, H is minus 1/2. We set G to 1. So, so Benini, Christopher, and Zaffaroni this was about almost 10 years ago, computed this, and it was also refined by many other people, but indeed showed that the log of the partition function of ABJM on S1 times sigma G with 1 unit magnetic flux is equal to G minus 1, the partition function on S3. So partition function on S3 is another quantity which is very, like whose computation is very important in the dual field theory. So they did one further passage, let's say, or at least this passage was made by another person, but in general, that's what it is. The final result that you get, you have to expand this also in the large N limit. So here you have 2 copies of Chern-Simon theory with the gauge group UN. So you have to take N large in order to make contact with the supergravity answer. But basically, at the end of the story, what you get by computing this via localization, by using these formulas, is that you get G minus 1 over 2 Gn pi, which is this is equal to the black hole entropy. So I skipped here, of course, the passages, but you can show, you can just look here in this paper how they compute it. But basically, it seemed that then these people achieved a match. And this was the first one that was achieved, a first matching for this kind of black holes in general. And they showed that the large N limit of the partition function of ABGM really reproduces the on-shell action of the configuration, which is also related to their entropy. So you have, let's say, an expression for the entropy of a black hole, which is non-trivial, which is means that the black hole has many states, in terms of a dual field theory, which is this one. Yes? It will change. So yes, this I was about to say it in the next 20 minutes. But basically, you will have, first of all, you will modify this factor here. But as I mentioned, you can also, to have a spherical event horizon, you need further scalars, which means that you have to consider a different background for a BGM. You need to also, here, the background is only, you consider a BGM, you couple it to a rigid background, S1 times sigma G. You need to add more background vector multiplets, because this would correspond to flavor symmetries. And this will take into account the fact that you have scalars and gauge fields in the gravitational action. So this, okay, just to precede what I was about to say, so you can also couple a BJM to background vector multiplets. So if you couple and change, you put S1 times S2 instead, you have log Z BGM. So it will depend on some parameters that I'm going to define momentarily. Okay, I wrote down everything. I'm going to explain everything in this formula just momentarily. So in general, you can, indeed, as I was asked, so you can modify this formula here by including other couplings in your background vector, in your background fields. Basically, you can couple a BGM to some fields which are non-dynamical. You can add further multiplets that, however, do not play a role in the dynamics. They automatically solve the equations of motion. So these background vector multiplets here will include, for instance, like a gauge field. These are indeed some matter that stays there, that it's frozen. And then also some fermions and some auxiliary field, for instance. Yeah, I'm afraid it's a lot of detail, but bear with me, then we don't need all of this in the following. But so these background vector multiplets, they have gauge field, they have some scalars, some fermions, and also some additional auxiliary field. The quantity, so the partition function at leading n order is this one, where all the deltas here, they need to be constrained to 2 pi in order for the partition function computation to be finite. And also these delta are made out of parameters in your background vector multiplets. So it's like the component of the component T of the gauge field in the background vector multiplets plus I sigma, which is the scalar in the vector multiplets, where I goes, in this case, from 1 to 4, because I couple to 4 background vector multiplets. So I chose this matter content on purpose, because it will correspond to a solution in supergravity with scalars. And the meaning of all this, I hope, will become very clear in the next 15 minutes. So in general, so this is all to say that here we have basically matched a number. So we got a number for black hole entropy, and we matched with a number that come out from the localization computation in your dual field theory. However, if you have other sorts of solutions, for instance, black hole solutions with additional gauge fields, scalars, and so on, you have entropy for those, and you can also retrieve it on the computation of the dual field theory. And some very nice mechanisms, such as the attractor mechanism, supergravity, and the eye extremization in the dual field theory are taking place. That is how I will explain in the next 15 minutes. In order to do so in order to achieve the dual of a particular black hole solution that I'm going to explain, you need to further couple a BGM to like a rigid background, which is more complicated with respect to sigma 1 times sigma g. So this is a BGM to 4 background vector multiplets on S1 times S2. I'm leaving here this formula. I'm afraid I was a bit too fast, but I'm going to now do the gravity side, and then we're going to compare. And hopefully many things will become at least clearer. But if you have questions, feel free to ask. Maybe it's good that I recap, maybe a bit. Okay. So for now, we have found some supersymmetric black hole solutions. We've seen that they have an area, and we have managed to reproduce the area also. We managed to reproduce it in terms of the thermodynamic potential, which is the supersymmetric, the on-shell action for the supersymmetric solutions, right? So we have seen that their on-shell action can be reproduced by a computation in the dual field theory, a computation that other people have done, that I allegedly have indeed discussed in very brief detail. You can use supersymmetric localization to compute exactly the partition function of a BGM on the boundary of your black hole, with a background that also has a magnetic field exactly the same as the black hole, okay? So this theory here lives on the boundary of the black hole, has the same boundary condition, let's say, and if you compute the partition function, you get exactly this partition function matches the black hole entropy. So you can see that you got a match, holographic match. You know where the states of the black hole come from. They come from this theory here. Well, in general, so that dates back to the whole point that in gravity, you have an entropy, but the solution is just unique. So in general, this dates back to what we were talking yesterday also with Alejandra, right? So the whole point is that in general relativity, you have a black hole solution, which is an ensemble. It has entropy, but you don't, so entropy means that you have many states, right, inside the black hole. But the black hole solution is just unique. Fixing the charges, you have only one black hole solution, right? So you cannot, so from the gravity side, you don't have these microstate geometries. Yes. Yes. Because I want to know what is responsible for this entropy here. So the entropy, like it's related to like the generality of states, right? So you want to know whether the states, where the states come from. So in gravity, you cannot have it. So of course, there are some other solutions which are called fastball solutions. So the fastball, so I'm not touching here upon the fastball program. People that believe in this problem, in this program, seem indeed like their aim is to find, is to retrieve black hole entropy directly in gravity by consider like a family of solution which doesn't have a horizon, which are called fastball geometries or microstate geometries. So maybe that answers your question a bit better. So the point is that, yes, in gravity, we have this uniqueness theorem. So we cannot really find, or at least unless you resort to these fastball geometries, which are still a program which is work in progress, you will not be able to count geometries and get this entropy, which is very, very big. You will get only one solution. So you need to do it on the field theory side. Yes. It's a trace over the ground states of the system. So you can see. So I didn't write it down here, but you can see this as the Witten index also of the. Okay, it's of the superconformal quantum mechanics that it's dual to this ADS factor in the near horizon geometry. So the ground states, yes. So it will be like, yes, you will need to, okay, it's a bit more complicated. I will need to spend a bit more time, but you can also see, like you can rewrite this partition function here as trace of -1 to the f e to the minus beta h. If you're more familiar with the trace, like with the partition function written in terms of traces. And so this partition function here acquires contributions only from the ground states of the system that are the ones that compose the black hole. Yes.
Just to be clear, the microstates that you are counting are those sort of matter fields that you can make?
Yes.
And this is a match between a semi-classical computation here and fully quantum.
Here, so I brushed a lot of details under the rug. So here, so the computation that I get from these formulas here, that other people got, of course, it's in principle fully like non-perturbative on. Here, I'm just comparing with the leading part, which is supposed to give you the classical part in supergravity. So I'm not putting here the function parameter just because I think it will complicate a bit of things, but you have other sub-leading terms that will contribute to quantum corrections to this entropy, to the semi-classical entropy that you have there. Which one? Here and here? This one will also have ... But I'm just focusing here on the expansion of the BGM action that will correspond to the leading term in the gravity side.
And you have mentioned that you need stream of black holes to be able to do these calculations. Where can I see that here?
No, I need the supersymmetric black holes. Yes, the point is that, okay, if you, that's another topic that, so in general, if you restrict yourself to a real metric, you have that supersymmetry implies that you cannot have a thermal solution with supersymmetry, let's say. So you can have an equisingularity as the solution that we saw yesterday. But so if you have an equisingularity, you have zero entropy, so it's not something that you're interested in. The case where you're mostly interested in is the one where you have actually an extremal horizon. You have an extremal horizon that preserves supersymmetry, then you can actually relate it, like count states via these formulas here. Okay, so I wrote down, yes, okay.
Maybe what I said is nonsense, but I just want to know if one can see this part as an IR limit of the supersymmetric.
Yeah, in general, so the solution here, let's say, the IR theory, so you will need to consider, so this solution here in the UV are ADS4, let's say, like at the boundaries ADS4. They flow to ADS2 times S2, and you can associate a CFT1, which is some sort of the IR theory that you get. It's like having this three-dimensional theory. You reduce it on sigma g, which is this thing here. You have a superconformal quantum mechanics, so a CFT1, which would be the IR theory. So you can do the counting here, and you get the same thing. Actually, the partition function that you're computing here, you can see that it's actually equivalent to the Witten index of the superconformal quantum mechanics that arise in the near horizon geometry. No. Okay, I'm sorry that I introduced this thing that now I have a bit of, how much time do I have? Maybe 10 minutes? 5 minutes. Yes, I know. It's more like I wrote down the formula for the matter couple, so for this one, and yeah, I mean, I can try to write down at least some of the properties of the solution to which I can match this particular partition function, but I think I will need to go a bit at least 10 or 15 minutes tomorrow. So I was mentioning that the matching that we have achieved from these minimal, like these very small solutions that we have here with hyperbolic horizon and so on, it is nice, meaning that we achieved the holographic matching, which is something non-trivial. However, we are basically matching two numbers, which is indeed non-trivial, but we would like to see a bit what is the, I mean, it's kind of interesting to see if there is more like physics to it that will actually happen in performing the matching between the free energy and the entropy of the black hole. So in order to do so, what we can do, like to get a bit more juice out of it, is that we can consider more non-trivial supergravity configurations, which have also further gauge fields. So and these gauge fields correspond to flavor symmetries in the dual field theory. That's why here I couple the BGM to background vector multiples in order to have flavor symmetries here, because this will correspond to some very to some other system in gravity. So, okay, that's a bit. So I'm gonna start here. So the solutions that. So here I give you a bit of a preview. So for the moment, just store this formula. So the solutions that we're gonna deal with, they will be a bit more. That will be dual to this setup there. Will be solutions to the n equals 2 gauge supergravity with vector multiplets. Vector. So it will be solution to this, like Lagrangian here. So it will be like a theory. Okay, the details are probably not super important at this point, but so this is another theory of supergravity. So before we had only Einstein maxwell. So we had the Ricci scalar. We had just a minimal coupling, so just one vector field, and we only had a cosmological constant. Instead here, we know that gravity comes with supermultiplets and so on. We coupled our theory to additional vectors. So that's why you have an index lambda, sigma, and here, and you also have, it means that you are adding vector multiplets. A vector multiplets contains a fermion, a vector, but also a scalar. So it means that you'll have further scalar couplings which are contained here. So there are lots of properties of this theory, which I think I don't have a lot of time to introduce, but just to get the matching to this a bit more explicit, let me mention that to specify the theory, we need to specify a quantity which is so-called holomorphic prepotential, which is a quantity like it's f. So it is a second-order polynomial in some variables which are called x. So let me also see that lambda goes from 1 to 4, while I goes to 1 to 3. And these lambda are nothing else other than homogeneous coordinates on your scalar manifolds, meaning that the scalars that are here, we just take it to be ratio of xi over x0. Maybe we can just put it here, let's say x4. Let's do it like this, x4. So your theory is specified in general by also, like, given this particular coupling here, you can derive, like, via the rules of special geometry, you can derive all, with a bit of effort, in the formulas, you derive all these couplings of your theory here. You can derive also, this is a metric on a special Kähler manifold. And in general, you can also solve the equations of motion of this theory, and you can impose preserving supersymmetry for some solutions which are indeed, like, they will be bigger solutions, but they will be very similar to the one that I showed you, that we worked with today and the day before. So maybe I'm gonna, okay, if I have 5 minutes, I'm gonna write down the solutions, so then we have the starting point for the remaining 15 minutes tomorrow, maybe. So again, so a BPS, so supersymmetric black hole solution. Reads like this. So if you see also in general, the structure really resembles the one that you have found without any scalar. So this is a solution of the theory with prepotential, which I wrote down here, square root of x4 of x1 to the third. So we have only one vector multiplet. Okay, I'm gonna erase this thing for the moment. Solution is also supported by, let's say, by, I'm gonna write it down here. Solution is purely electric, as we saw for the exotic monopole, but also like it has a magnetic field. Okay, let's call lambda. So the only field in your configuration, it depends on the radius. And also you have some constraints between the value of P and the parameters that parameterize this scalar field here. So important point to notice here is that in general, you have that the solution is characterized by the presence of this beta, okay, B1 over third. So the solution is very similar to the one that we have found for the exotic monopole solution. It's a purely magnetic solution. It's also 1/4 BPS. You can find the Killing spinor again before, purely magnetic, and the presence of a non-trivial scalar in your configuration, which means that B1 needs to be, in general, non-zero. In order to have a scalar which runs through the entire configuration, makes possible the fact that C is negative. So if B1 is sufficiently positive, this parameter C is negative, and thereby you have a horizon here. So this means that indeed, once you have your scalar turned on, there are specific configurations, you can have a solution which preserves supersymmetry with a spherical horizon, and also that has, like, with a spherical section that also has a horizon. So the entropy of this solution here, I promise that I have almost finished. It is written in terms of the sections. P lambda over xi. So apart from some multiplicative factors which are like in front of this should be like something, this should really look like the formula that I showed you before for the BGM partition function with background vector multiplets. And there is a reason why is that, but I'm gonna leave you on a cliffhanger, so then I will explain you tomorrow. So there are specific extremization principles that are valid for these sort of solutions. So you have an extremal configuration with scalars, and whenever you have an extremal configuration, this black hole like acts as an attractor, meaning that there is an attractor mechanism that fixes the scalars at the horizon to a specific value, which is obtained by extremizing a particular function. And we will retrieve the same extremization principle once we compute the partition function in dual field theory. So in general, all these things that I showed you, like at least the last part, which seems a bit complicated, I will take it back tomorrow. But this is just to show that indeed, by computing the partition function in a dual field theory, and by comparing with the mechanisms that are in act in the supergravity configuration, we'll see that there are different extremization procedures that are exactly mirrored in the dual field theory and on the gravity side. So yes, for the moment, yeah, I'm sorry for this abrupt departure, but I'm gonna take it back for
No, it's
tomorrow.
okay. I didn't want it to catch you, sorry.
Yeah.
We thank Chiara. Two questions. Well, we have time for two questions, perhaps.
Yes, so yeah, I thought, so okay, this was very, very fast the last time, the last part. So x1 are projective coordinates, so you can think of it as just functions of, like function that parameterize I mean, like coordinates that parameterize your scalar fields. So the scalar fields in your game are these Z, which appear in your Lagrangian. So they are in general, yes, so they are sections of a symplectic bundle that you find in the structure of supergravity, but in general you can think of it only as projective coordinates. The point is that when you rewrite the entropy in terms of this section, you have a very suggestive form, which is very similar to the partition function of the dual field theory that I showed you before here downstairs. So tomorrow I'm going to show that there exists an exact mapping between the parameter of the supergravity solution here and the one that appeared in the partition function of the dual field theory, and both the entropy of the black hole and the partition function of the dual field theory are extremized. They are subject to two different extremization principles. One are the attractor mechanism, the other one is eye extremization, that are really mirroring each other, let's say. And due to this, let's say, extremization principle, you will get an exact matching between black hole entropy and the twisted index or this twisted partition function of a BGM.
Okay, any other really burning questions? Yes.
So how did the people arrive to this result, to the black hole entropy? By
So
the area?
No. So for this one, you basically have to compute the area that comes from this factor here.
Okay, so
you have to express the area that you have here in terms of the charges, and that's what this extremization does.
okay, thanks.
I mean, I was very schematic here. Tomorrow we can just do it in more detail. So tomorrow I'll need maybe 15 minutes to explain these extremization principles, and then we can, at least it's going to be a bit more self-contained.
We thank Chiara again. We meet again at 2:30. At 2:30.